Hello everyone, and welcome to MacDermid Enthone's discussion on the basics of anodizing. My name is Robert Collin. I am the America's Technical Manager, and I will be the moderator for this event. The presenter is Sasha Wegner. He is our Anodizing Product Line Manager. Please submit any and all of your questions in the question box of this webinar. We will answer your questions live after the session concludes. If we cannot get to your question, we will get back to you via email. Again, thank you all for taking the time to learn about the basics of anodizing with MacDermid Enthone. With that, Sasha, the session is yours.
Thank you very much, Rob, and good morning to everyone attending the Basic of Anodizing training session this morning. As Rob mentioned, my name is Sasha Wegner. I've been with the company for over 20 years in many different roles, and lately I have taken over the role as the product line manager for Anodize in the Americas. So what we're going to do today is we're going to have a very basic fundamental anodizing course, and we're going to start looking into the background of aluminum as a substrate, and then from there we will move on into some applications and then into the individual processes. And what I want to do is go into a little bit more depth into these processes, the mechanics behind the processes, what they actually do, why we actually need them, and how we can select the right processes for the right application. A little bit about the application for aluminum substrates, and I think most people are very familiar with the market segments here. Architectural is by volume the biggest market for aluminum and aluminum treatments. And these aluminum components, they go into the curtain walls, shower frames, window frames, door frames, a lot of extruded profiles. So the requirements here are very, very high. They obviously have an aesthetic, they got criteria they have to meet. They have very, very high corrosion standards as well, especially when we think about curtain walls. Once they go up on a building, they're very difficult, close to impossible to remove and take down for any sort of maintenance. Another big segment for the aluminum treatments is the automotive industry. Again, aesthetics here and very high corrosion resistance, probably even higher than the architectural industry, with new requirements coming in on pH resistance, on cyclic corrosion, so on and so forth. Another important segment, the engineering and consumer goods. And what we sort of group under that segment is anything from heat sinks, electronic components, light fittings, reflectors, so on and so forth. Sporting goods as well, a lot of dyes, organic dyes involved in these applications. And then last but not least, the aerospace industry. Again, very high corrosion resistance, not quite so much aesthetics here, but it's really all about corrosion protection, wear resistance, so on and so forth, keeping planes up in the sky. When we look at aluminum as a substrate here, it has a very low density, and that makes it very, very attractive for us as a lightweight material to construct planes, cars, any sort of assembly from aluminum to save weight with its obvious benefits. It also is a very good conductor. So anywhere where we need electrical conductivity or thermal conductivity, aluminum is a very good material to use for that. It protects itself through an oxide layer, and this is an oxide layer that occurs naturally on the surface. and when removed through scratching, it will actually self-heal, self-protect itself. It's a very, very thin oxide layer with a limited corrosion resistance, but it's one of the benefits of using aluminum. Recyclability, one of the big phrases at the moment. There are statistics that all aluminum that is in circulation at the moment has actually been, or 70% to 90% have actually been produced from recycled aluminum. So a very, very high percentage of aluminum we can recycle, we can reuse, and again save energy. So one of the downsides using pure aluminum is that it doesn't have a high strength, and when it is treated, it will actually self-anneal or lose strength in itself. So a way around this self-annealing problem and the softness of pure aluminum is to alloy the aluminum. And this alloying components will provide hardness, better wear resistance, and it will give some of the alloys the ability to actually be heat treated to even further increase the hardness. So when we look at the different alloy constituents here, there are some alloy designations, and I think everyone who's treated aluminum alloys, one of the first questions that I ask is what type of alloy are we actually dealing with, and this is where these designations come into effect. And when we go from the top down, we have the different series here, the 1000 series. This is an aluminum alloy that is actually unalloyed. This is just pure aluminum, and it is predominantly used in the food industry. It is used for reflectors and also for electrical conductors. Again, we're using the pure aluminum without any alloys to get the best electrical conductivity here. When we go to the 2000 series here, the alloying element here is copper. This is a aluminum alloy that is predominantly used in the aerospace for a structural component. The copper gives the aluminum extreme good strength. It is a heat treatable aluminum alloy as well. Not easy to anodize, but for the aerospace, it's one of the main alloys they use. The 3000 series here, alloyed with manganese. This is for sheet material, for trailers, anything that is cladded, and for some of the packaging materials as well. 5000 series, magnesium as the alloying material here. Again, this is used for some sheet material. There is for the architectural industry, bright trims for cars, so on and so forth. The 6000 series here, that's probably one of the most common alloys we come across. These are extruded alloys, alloyed with magnesium and silicon, especially in the automotive industry and architectural industries. This is what's used for doors, windows, cladding, so on and so forth. Then we have the 7000 series here, alloyed with zinc, magnesium, and a little bit of copper. Again, for structural components, heat treatable, very high strength, and fatigue resistance here goes into the aerospace industry, some automotive application, and actually watches and phones. So those were the wrought aluminum alloys. The same applies to cast aluminum designations as well. So we look here at the 200 series which is alloyed with copper for strength, 300 series silicon, copper, magnesium, 400 series silicons, and 500 series is alloyed with magnesium. I think the most cast qualities we come across and that are really important for us will be the 300 series. There's a lot of brake components that use the 300 series. Now with the EV battery boxes, there are also some automotive OEMs who have chosen cast aluminum for these battery boxes. So when we use aluminum alloys and alloying materials, there are some disadvantages, and the main disadvantage really is by alloying aluminum, we lower the corrosion resistance, or its natural corrosion resistance. And because of these alloying materials, they will actually form intermetallics, or they will precipitate within the alloy itself and create a not always homogeneous alloy or appearance on the surface. So that can have certain problems with corrosion. It can have problems with wear resistance as well. So to get around this problem, there are different ways. In the case of corrosion resistance, we can just treat them with passivates. If we wanted to increase the corrosion resistance even further and actually give these components some sort of wear properties, anodizing is really the process of choice here. And this is what I want to focus on for today. So if you look at the anodizing process in itself, it's relatively simple, and it always follows the same process sequence here. First of all, we have a cleaning step, and after that cleaning step, there is a we have to choose a certain way for these components, depending on the final appearance and what is required. So some parts, if we start here on the right, will actually have a high specular requirement, so they might go through a chemical or electrochemical polishing sequence. Some components, especially in the architectural industry, they require a satin effect or a dull matte effect. That's really done to hide some of the extrusion lines. So they would follow through a satin etch or an E6 etch here. Other components that really just need to meet general requirements, they might just go through a normal alkaline etch to remove the oxide layer. From there, it follows pretty much the same sequence here. We go through a desmut or a deoxidation process, then through the anodizing process where everything really happens, and then optionally coloring, and the final process step here is the sealing, and that's really where the pores we generated are closed up. We're locking in the color, we're providing good wear resistance, and especially we are protecting the component from any sort of corrosion. And the corrosion resistance we can achieve by anodizing these parts is phenomenal. So this is what it looks like as a process flow. If we were to design an anodizing line, again from the cleaners, then the choice of bright dips or satin etches, going through the deox, the anodizing, coloring or dyeing, and then through the sealant and the final rinses. For everyone who hasn't seen an anodizing line and the size of some of these anodizing lines. I've got some pictures here of an architectural line. And these profiles we see here, bottom right, these are 30 feet long. The work envelope, the tank width is phenomenal in some cases, going up to 40 feet. So these are very, very large size components and profiles we do here. Let's jump right in with going into a little bit more depth of the cleaning and the degreasing and the subsequent process steps here. I think everyone who's been involved in electroplating, and I presume this is most of the people here on the call, know the importance of cleaning and degreasing. So this is really to remove any residues, any soils, oils, cooling liquids from previous operations, whether that is from the extrusion, polishing, forming, or any sort of machining here. So these have to be completely removed to make sure that we have a good attack from any subsequent process step. So what's also important is that we have a minimal attack on the surface here. And these cleaners are specifically designed to meet these criteria. I think everyone knows that aluminum is a very sensitive base material. It easily gets attacked by acids or by alkaline. So we have to pay attention to how we formulate these cleaners. There are different types of degreasing when it comes to aluminum. I think it all very much depends on the final optical requirement, depends a little bit on the alloy we're treating, and so on and so forth. Some of the degreasers are alkaline degreasers with a high alkalinity, with a pH above 9. These actually will have a certain attack on the surface. It will dull off the aluminum. They are effective cleaners, but as I said, as I mentioned, they will dull off the components. I think the most commonly used cleaner for aluminum are the multi-alkaline degreasers, and these are based around about a pH of 9, and they hardly have any attack on the surface. So they're very well pH buffered, they're inhibited, and we see immersion times of up to half an hour, a few hours without any attack on the surface. The third group is the acid degreasing and the acidic cleaners. So they're mainly based on phosphoric acid, sulfuric acid, any other sort of organic acid, and surfactants as well to remove and emulsify and suspend soils and oils on the parts. So when we talk about the effectiveness of a cleaner and how to assess if the cleaner in the anodizing line actually works, there are two ways of doing that. One is actually walking up to the work after cleaning and rinsing and observing any water breaks on the surface. What we normally look for is a completely wetted surface. We want a closed water film on the components, and not what we see here in the picture, where we have little droplets and islands of water distributed across the surface. This will really show us that there's still oils remaining on the surface that need to be cleaned. The second test here is the white tissue test. This is mainly used for residues, solid residues, any sort of dust, metal swarf, abrasion products. And what we do is we just wipe with a white tissue. We look at the tissue and see if there's any white, any black smuts left on the surface. Again, if we do see any residues, then that would be an indication that the cleaner is either not suitable for that particular residue, or they might be too old, or they need strengthening. The effectiveness of a cleaner, I just touched on it. It really depends on the type of soil we want to remove. So not every cleaner will be effective for every residue, every oil, grease, polishing compound that needs to be removed. So there's a few tests that need to be done prior to installing these cleaners. Obviously, concentration. We can increase the concentration up to a reasonable high limit before we see any etching on the components, or before we actually go so high that the surfactants will oil out of a solution. Temperature, again, the higher the temperature, the better, but we are limited with the attack on the aluminum surface here. So normally 65 degrees Celsius is a good benchmark for cleaners. Immersion time, again, this is very much dependent and dictated by our anodizing line and how much time we have available in the cleaners. The longer, the better, without having any attack on the surface. One very, very effective way of increasing the effectiveness of our cleaners is introducing air agitation. Any sort of movement, any sort of exchange of the solution on the part, on the component, will actually help removing these solids, oils, greases, so on and so forth. Ultrasonic, on probably everyone's wish list, very effective removing polishing compounds or any sort of other residue on the surface. If we look at the products available from MacDermid Enthone here, we have our go-to products. There are many other products available, but these are really the ones we would use as a first port of call here, and our go-to product. C14 as a liquid cleaner, mildly alkaline. There's no edge, there's no boron, so from an environmental perspective, very suitable as well. Obviously, no silicate. It's very highly wetted, and it's a very, very effective cleaner. If someone prefers powder products, we have the Oxidite C8 here. Again, a mildly alkaline cleaner, non-silicated, non-edge, highly wetted, and a very, very highly efficient cleaner here. For certain applications, certain alloys, if customers require and prefer an acidic cleaner, we have the Oxidite C20 based on phosphoric acid. It's a medium wetted system, again highly efficient in doing the job. So the next step here, I want to touch a little bit on the etching. And the main purpose of the etching process itself is the removal of the natural oxide layer that forms on the aluminum. So we talked about that before. This is a self-healing process, and this needs to be removed prior to anodizing. And this is what the etching solutions really do. We also use the etching process in the architectural industry to remove a lot of aluminum surface to hide surface defects. And these surface defects come really from the extrusion process itself, from the dies and those flow lines we sort of introduce or put onto the aluminum profiles. The different types of etching processes here. we've got the alkaline etching processes, very, very easy to run, very well understood, and relatively cheap as well. And then on the other side, we have acidic etching processes as well for certain aluminum alloys and certain process sequences where customers prefer them. The acid etching process is really based on sulfuric acids, phosphoric acid, and or ammonium bifluoride, especially when we have to remove a lot of aluminum from the surface, like the architectural industry. We tend to use something a little bit more aggressive, like the ammonium bifluoride based etches here. They do dissolve a lot of aluminum. They precipitate it as aluminum fluoride. But what they really do is they do not they attack the alloy evenly. So they're not selective. They're not just etching away the aluminum and leave the alloying constituents on the surface. They will actually dissolve all of those, and the metal will actually look much cleaner after an acidic etching process. And I put that here. They actually reduce the amount of smut on the surface. Some of the disadvantages, especially when we deal with ammonia and fluorides, they cause problems in the wastewater stream. Some customers are restricted in terms of ammonia they are allowed to handle. Also, the fluoride has a very aggressive nature, and there's a huge attack on any plant and equipment and structural component around the anodizing line. If we look at the alkaline etching process, and this is the two different ways of setting them up. The first one is really for a non-defined finish, and this is when we look at this, it's more like a stripping etch, where we strip our racks, where we can strip our rework if we do create rework, and it will just remove the aluminum oxide for reprocessing. They're made up at a relatively low concentration of around about 50 grams per liter. They use an etching additive which complexes some of the aluminum and alloying material, so it doesn't precipitate in the solution. Operate around about the 55 degrees Celsius mark. On the other hand, when we are dealing with the architectural industry, when we are dealing with finishes that have a defined matte effect, we have to be a lot more careful how we run these processes. And in the architectural industry, we're talking about an E6 finish. And that is a very defined, a very smooth, almost like a pearl bright finish, if someone knows that from the nickel chrome industry. And those finishes can only be achieved by using very high concentration of sodium hydroxide and very high concentration of aluminum. And these processes will reach an equilibrium, but that still needs to be maintained very well. So it's very important that we analyze for the sodium hydroxide, the aluminum content, and very much the etching additives as well. Not everyone is actually able to analyze for these etching additives. Sometimes when they go out of balance, we can see precipitation of the aluminum etch here, and that's normally the death of the bath. If anyone has come across this, they need to be pumped out or dug out and replaced, and that can take a considerably long time to get up to the required amount of aluminum again to be back in production. So these aluminum etches, alkaline etches, they're based on sodium hydroxide, potassium hydroxide. There's some chelating agents in there to make sure that the aluminum does not precipitate, and there are also some accelerators to facilitate the removal of aluminum from the surface. They need to have some additives built into the formulation to actually complex the zinc as well. Zinc from some of the alloys will re-precipitate onto the surface, and it will leave sparkly star-shaped little areas which are very visible after anodizing. And if the etching additives are not designed to complex these zinc contaminations, you might find yourself in a lot of trouble here. One of the downsides from an alkaline etch is that it will actually form etch smut. And I touched on that before. The alkaline etches are very selective. They will attack the aluminum predominantly and leave the alloying components such as copper and silicon left on the surface. And this will create this very dark gray, almost black smut, which needs to be removed in the deox process or the desmut process. And that's why for any sort of alkaline etch, we need the subsequent desmutting and deoxing processes. When we look at it on a more schematic drawing here, we selectively remove the aluminum here, what we see at 0 minutes, and we work our way down, and through this process we actually liberate and surface more and more of the alloying constituents on the surface. And this will really result in these very, very dark, almost black panels you can see here at the bottom right. And this literally is just silicon, magnesium, some copper and zinc on the surface. So, as I mentioned before, the etching additives is a very important part of the process. We can analyze for these additives as well. They come in liquid form, and we have two different additives we can provide here. The E26 is literally just the magic, the fairy dust. Contains all the active ingredients, the accelerators, the complexing agents, so on and so forth. It's added to the sodium hydroxide. Customers have to provide them themselves. On the other hand, if someone prefers that we provide the whole process and they just pour it over the side of the tank as a one-shot additive, we have the E22. This contains all the caustic, all the etching additives, and it can go straight into the tank and just needs to be diluted by water. A little bit about the brightening solutions here, and everyone who has a brightening process or has come across some of these applications now, there are a couple of different processes available. They're not all easy to run, and they all have their downsides and their benefits. I'm just trying to sort of point them out a little bit as we go along. The two main categories here when we talk about brightening is we have a electrochemical brightening process. These use big rectifiers with a high output on the voltage and the amp side. We're talking up to 25-30 volts, starting amperatures of around about 10-15 amps per square decimeter. So they're very, very big rectifiers, and that limits really the size of the application. So for big profiles where we're processing square meters rather than, you know, on the scale of decimeters, this wouldn't be feasible to build rectifiers that size, or even just the heat generation from applying the currents would make this unfeasible. For those applications, we really prefer chemical brightening dips. And for the chemical brightening dips, again, the two subcategories: one that works with nitric acid. These are really the traditional brightening dips. The one we know that create all these brown fumes, the nitrous oxide fumes, very toxic. They have they need very good extraction. They need fume scrubbing, so they tend to be quite expensive in the way they need to be run. And then just lately we had a few new processes come through that actually cut out the nitric acid, work without nitric acid, obviously with the beneficial result that we don't have nitrous oxide gases, we don't need the fume scrubbing, so on and so forth. But these processes are not quite as bright. They're more semi-technical bright process. So again, this is a little bit what I explained before. The immersion times, they really vary from anything from a minute to 10 minutes, probably closer to 3 to 5 minutes for the chemical brightening dips. They run at extremely high temperatures, around about 100 degrees Celsius, so quite cost intensive. The electrochemical brightening, we see this here. We're having a currents of 25 amps starting currents, very high voltages as well. They run a bit lower in temperature, but the processing time for an electrochemical brightening process will be significantly longer, anything up to 15 to 20 minutes. So the way it works when we look at the a micro profile of an aluminum component, we see all these peaks and troughs above this yellow line here. And what we try to do is we're trying to smooth this out. So we're trying to remove those peaks, bring them much closer to the troughs, and this will actually reduce the scattered light and give us the appearance of a much brighter, much more reflective substrate. When we look at the chemical brightening as a process and the mechanics behind it, there are two competing actions. And when we look at the formulation, we have nitric acid in these processes, we have phosphoric acid in the process, and some metal brightness. So the nitric acid in the process actually forms an oxide film on the aluminum, and it protects the surface, and it will actually stop the dissolution, and that's exactly what it's designed for and what it's supposed to do in this system. The opposite reaction here is from the phosphoric acid. The phosphoric acid actually is the part of the system that attacks the aluminum surface and what dissolves the aluminum. And because of these counteractions here between the nitric and the phosphoric, it will actually work towards removing more aluminum from the peaks. The troughs and those little recesses are actually a little bit more protected because the agitation around those areas is less. The oxide film is not removed as quickly as from the peak areas, and therefore we have more attack on the peaks of this profile. And that over time will actually guarantee that the troughs are removed in a higher rate than we attack the surface in those troughs or recesses. And as I said, and this over time will smoothen out the surface. What we also have in some of the formulations are metallic brightness. And I think one of the most commonly used one is copper here. If we introduce copper in the solution, and because of the electrochemical potential between copper and aluminum, it will precipitate onto the surface of the aluminum. And again, through that, it would stop the reaction. What happens here, and again, because of the agitation, the copper will precipitate or will remain in those recessed areas, in those trough areas, because of the lack of agitation and solution movement in those areas. And therefore, the attack on peaks and is higher, and therefore the removal rate of those areas is higher. And again, we're smoothing out, we're leveling out the surface profile. I was touching on the nitric-free processes before, and I think after we sort of going through the mechanics of what happens in these solutions, we can understand why we will never achieve a very high gloss finish with these processes, because of the lack of the nitric acid and the oxidizing constituent of the system. So the nitric acid is obviously substituted by other chemicals, and what we see here really is these nitric-free processes have a particular application. They're not really done or they're not really used for light reflectors where we need that very, very high specular glossy finish. These are really done for components, for extruded parts, for lineage parts that need just brightening up a little bit, just to lift that surface to make it a little bit more attractive. And that's really the market segment we're targeting with this process here. And you see quite nicely from these pictures here, you know, we start with a very, very dull surface here, and we end up with a nice specular, semi-bright, technical bright surface. And obviously one of the benefits here is, again, no nitric acid, no nitrous oxides here. We don't need fume scrubbing or any dedicated effluent treatment for the wastewater. The product available, Oxidite Bright, really the standard process for a very, very glossy finish, nitric acid containing. We have the Oxidite Bright NF. NF stands for nitric free, semi-gloss product. And then the Oxidite Electro Bright with this, which is our electro brightening process using rectification, so on and so forth. All these products come as a liquid. They're hex chrome free and environmentally friendly as much as that can be with those processes. As I mentioned before, the deoxidation and the desmut. This is really designed for the removal of alloying material. So when we go through the alkaline etches, we dissolve the aluminum, we have the alloying material left on the surface. They need to be removed. And we can see here on the right are different alloys, and they will give different degrees of smut on the surface after etching. So it also removes the natural oxide layers, any sort of scale from previous process steps. Those parts have been through. It really, it's an activation. It's an activation and conditioning of the aluminum surface prior to anodizing. Some customers actually use it to break the seal for components that need to be reworked. So it cracks open the pores, it attacks the initial surface, and then it makes it a lot easier to strip the anodizing coating in an alkaline etch afterwards. Sometimes when something went wrong with the coloring, with the dyeing of aluminum anodized components, we can actually use those solutions to remove the dye from the surface, from the pores, and actually go back through the dye itself without reworking and re-anodizing the components. So the deox, they're really a mixture of non-etching acids like sulfuric, nitric acid as well, and some strong oxidizers if required. Some of the systems, if we work with a lot of silicon-containing alloys, contain a small amount of fluoride to make sure that this silicon is removed. And what we always say, we have to understand that formulation. If we do have fluorides, we have to pay some attention to tank material and the surrounding of the deoxidation tank. Again, there's a deox for every application. There's a specific deox for more complicated alloys, higher alloyed aluminum substrates. So we see the picture here from, this is really what we ended up with after the aluminum etching. We have all the alloying components on the surface, which resulted in that very dark gray or black smut on the surface. Through the deoxidation, those alloying components are dissolved and removed from the surface, and we end up with a very clean and smut-free panel here or component. And again, white paper test is a good test here. Just wiping across, see if we leave any traces on the component, which would suggest that there's still smut on the surface, which then in turn will give us problems in the anodizing and probably further downstream in the dyeing and sealing processes. So the products we've got here are really two products. One is an iron-based deoxidizer, desmut, the D30. There's a can be used for all general applications. It works extremely well. It comes as a liquid. It is a one-shot additive and diluted with water. It contains a little bit of nitric and obviously ferrous, and it's a long life product. If someone had concern about the use of nitric in their anodizing line, then the D34 would be the answer here. It is based on sulfuric acid. Customers have to supply the sulfuric acid here. The D34 is added to that and to the water. But the benefit of the D34 is it's completely nitric free. And again, peroxide based, a long life process and product. And this really brings me to the end of the session today. It was the part one. We covered everything from the substrate to the anodizing process, and today we have managed to go all the way up to the deoxidizing. We have planned a second part of this basic anodizing training, and we'll confirm the dates and the times for that. And through that second part, we'll cover the anodizing itself, some of the additives we can use and the benefits of those additives. We'll cover the dyeing process, and we will spend a little bit of time on the sealing process, the different sealing processes for different applications, and then we'll end up with some quality checks and how we can guarantee that the parts will actually meet the final specifications and requirements. And as Rob said at the beginning, if you have any comments, any questions, any suggestions, please use the email here on the last slide, Sasha Wagner at MacDermidEnthone.com. We'll be more than happy to get back in touch with you, try to answer all your questions. And yeah, I hope you enjoyed the session today.
So Sasha, thank you very much. It was a great session on the basics of anodizing for the pre-treatment prior to. All of the questions that have been submitted today, we will get back to you via email within a day or two. That said, thank you very much, everybody, for attending. Enjoy your day, and please stay safe.